Hey, everybody. So the last section that we have for this chapter is section 8.9. We're going to be talking about infinite integrals. So sure, these should be infinite integrals that we're talking about here. And these integrals basically are integrals that you have either an infinity as a limit of your integration, or you're bumping up against an asymptote. And if you bump up against a vertical asymptote, it's possible that asymptote shoots off to positive or negative infinity. And the surprising thing is, even though a lot of these areas have infinite sort of width or infinite height, they are finite numbers. So the area underneath a curve is actually finite, even though the amount of width of that area is going to be infinite. So that's the idea. So how do we figure this out? So what we do is we actually turn this limit into, or sort of turns integral into a limit. And so I don't take the limit, don't take the infinity and plug it into anything, because that's not a possibility. We don't plug infinity in as a number. It's not a number. It's this concept of growing without a bound. And so that we want to capture by taking the limit as something goes to infinity, and then that something is what replaces the limit. So here, the limit of integration, excuse me. And so what we do here is for instance, I'm taking the integral from a to infinity of some function. I turn that into the limit of b as b goes to infinity of the integral from a to b, and then I have f of x dx in there. And so then I do that integration. And then I plug in that upper limit of integration as b. Then after I've got that all evaluated out, then I take the limit as b goes to infinity. So let's do an example of this. So I have the integral of 1 over x squared between 1 and infinity. So I turn this into the integral from 1 to c, as c goes to infinity, of x to the minus 2. So I just sort of turn that 1 over x squared into x to the minus 2. Now I do the antiderivative. So the antiderivative of x to the minus 2 is negative x to the minus 1. So I have x to the minus 1 over minus 1. And I evaluate that between 1 and c. And so I plug in the upper limit of c, and I have these backwards. So this should be negative 1 over c. And negative 1 over 1 as the lower limit. And so now as c goes to infinity, I should get negative 1 over c goes to 0, because it's a negative 1 over a really big number. That really big number, as it gets bigger, this fraction gets smaller and smaller and smaller and gets closer and closer to 0. So that ends up being just 0 on the top. Minus negative 1 is just positive 1. This is sort of a plus 1. So that sort of, let it sink in for just a second here. What does that mean? That means the graph of 1 over x squared, which looks something like this, sort of the volcano-y thing. If I take the area from 1 all the way to the right, that area inside there is only 1. So it's 1 square unit of area inside that infinite region, because it's decaying towards 0 fast enough. So that's the big kind of thing to think about is the question here will be, is the function that we're trying to do the antiderivative of, is that decaying fast enough so that this area becomes a finite number instead of an infinite number? And so that's the idea. Okay. So in this situation, yes, it did actually work out. It's possible that this doesn't work. So let me do an example. So 1 over x. So now this function, 1 over x, looks something like this. I'm doing this, asking the same question. So what's the area of the region from 1 to positive infinity of this 1 over x function? Okay. So I sort of think about this a little bit. I integrate. First, I turn it into a limit. So take the limit as c goes to infinity of 1 to c, the integral from 1 to c, 1 over x. The antiderivative of 1 over x is natural log absolute value of x between 1 and c. Well, c is a positive number because it's going towards infinity. And so you're doing it natural log of c minus natural log of 1. 1 is also a positive number. Natural log of 1 is 0. And now as c goes to infinity, natural log of c goes to infinity as well. So this says there's an infinite area underneath this curve from 1 to infinity. Okay, so the curve 1 over x squared was decaying fast enough. This curve 1 over x is not decaying fast enough. Now, there are, as with many things infinite, lots of just uncomfortable situations to be in for this. So infinity is not a comfortable place to live. And we definitely don't like having infinite stuff going through. So one of the things that I want to sort of mention here, all right, so that's great. So 1 over x, that area is too big. So what I'm going to do is I'm going to take that region that I just had. So the region I just had was from 1 to infinity, and it was the function 1 over x. I want to take that region and I want to revolve it around the x-axis and create a three-dimensional object. Okay, so you would suspect, right? This is an infinite area. So if I revolve it around the axis, it's certainly going to have an infinite volume, probably going to have an infinite volume. That's sort of one of the things that you expect of the world, right? So something infinity should stay infinite if I do something else to it and make it even bigger. In particular, this is actually a bigger amount of area that I'm sort of capturing in here, but it's actually a volume, right? So okay, maybe. So let's try it. So, okay, so I've got that area under that curve. I'm going to revolve it around the x-axis. So to do that, I take pi times that thing squared. So it's the disk method, pi times r squared, and that's the function value. So the function squared on the region from 1 to infinity. And then I want to integrate this thing. But wait a minute. This is really pi times the integral that we had at the beginning. And the integral that we had at the beginning evaluated to 1. So what in the world? Oh my gosh. So what we got here is the volume of this region between x equals minus x, y equals x to the negative 1, from 1 to infinity, revolved around the x-axis, is not infinite. It's pi. Even though the area underneath this curve, x to the minus 1, is not finite. It is infinite. The volume that we get by revolving it around the x-axis is actually pi. So it's pi units cubed. So this is one of the things that's sort of unsettling with infinities, is that these limits exist in some situations and not in others, but it doesn't seem to sort of correspond to each other. The one that's not there, the volume that seems like it's smaller than the volume that seems like it's bigger than this area is finite, but the area itself is infinite. And so there's a little bit of unsettling information that we get out of these things. Okay, so we get a bit unsettled with the infinities, but as long as we do our limits and sort of think of things correctly, we're going to end up getting the right answers out of these. So in general, if I have 1 over x to some power, that will be finite if I integrate from 1 to infinity, if that power is bigger than 1. If it's a big enough power, this is going to be finite. And you can sort of think about this, but what is that actually doing? Well, the antiderivative of 1 over x to the p has a denominator if that p is big, and has no denominator if that p is small. Right? And so if it has a denominator, the limit as x goes to infinity, as that thing goes to infinity, will be 0. So that will give us a finite limit in the end. If it doesn't have a denominator, if it has a numerator, power of x, so that numerator power of x will go to infinity as x goes to infinity. So this is sort of what we have. So if I have a big enough power on the bottom, it's finite. And if a small power on the bottom, it's going to be infinite. Next, we ask, what about an asymptote? So I think again about my same situation, something like 1 over x maybe, but 1 over x has this asymptote that is at 0. X cannot be 0. What if I want to integrate right up to that limit, right up to that point? So what I do is I take the antiderivative and I again turn that integration, that limit of integration that has a problem, that problem spot, into a variable, and take the limit as that variable approaches that problem spot. This time, you'll notice I have to do that limit as it approaches it from one side or the other. So here, if a is the bottom limit and a is the asymptote, I take the limit as that variable c approaches a from the right, because I'm talking about coming at it from the side of b, and b is bigger than a, so I'm coming at it from the right. If I come at it from the left, that's going to be at the top limit. So the top limit is the asymptote, then I have to do that from the left. Okay. Sometimes it's finite, sometimes it's not, just like the other one. For example, 1 over square root of x has an asymptote at x equals 0. So at x equals 0, this is undefined because the denominator cannot be 0. And so I have to take this sort of antiderivative like I want to. So I want to do the limit as a approaches 0 from the right. And we're really lucky here because as a approaches 0 from the left, this is not defined because the square root of a negative number is not defined. And so it doesn't make sense. But here I'm only doing a right-handed limit, only from the right, because 1 is bigger than 0. So I'm coming at this limit from the top. So we're saying from the right, the limit from the right is going to be what? Now I do the antiderivative. The antiderivative of 1 over the square root of x is just 2 times the square root of x, evaluated between 1 and a. Plug in 1, plug in a. And now as a goes to 0, this a, 2 square root of a goes to 2 times the square root of 0, which is just 0. So I get just 2 times the square root of 1. This is 2. So the area between the curve 1 over square root of x and so between 0 and 1 for the function 1 over square root of x is just going to be, so this area is just 1. So 1 unit squared inside of that area. Again, this sort of means that we're approaching the asymptote fast enough so that we decay fast enough to 0. So it's essentially getting closer and closer to the axis, and it's getting closer to the axis fast enough that it's going to give you a nice finite limit or a finite area inside of there. And so that's good. If I have an asymptote and I'm sort of evaluating across that asymptote, then I actually have to split my integral into 2 pieces and then take 2 separate limits. So for example, the integral from 1 to 10, the asymptote for 1 over x minus 2 to the 1/3 is at x equals 2. That's where the denominator is equal to 0. So I have to split my integral into 2 pieces. It's the integral from 1 to 2 and the integral from 2 to 10. The integral from 1 to 2, I'm going to take a limit to evaluate that one. So it's the limit as a goes to 2 from the left, integral from 1 to a, 1 over x minus 2 to the 1/3. And then the limit on the other one, so 2 to 10, is the limit from as c goes to 2 from the right of c to 10 integral 1 over x minus 2 to the 1/3. I do a u substitution in here, let u equal x minus 2, du is dx, so I'm sort of happy with that. The antiderivative of x minus 2 to the, or u to the 1/3 is just going to be u to the 3/2 u to the 2/3. Evaluate between 1 and a, limit as a goes to 2 from the left. And you'll notice that sort of, oh, and I guess I have to be careful there. That's really 1 minus 2 is -1, and a minus 2 is the top limit. So this turns into a positive exponent. So it has something in the numerator, and as a goes to 2 from the left, it's going to go towards 0. So this top limit is going to go towards 0. Same with the bottom limit of the other one. So the integral is exactly the same. It's just 3/2 u to the 2/3, evaluated between this time c minus 2 and 8. And now I evaluate both of those things at in this case, -1 and at 8. And then I add those two together, take the limits as a goes to -2 from the left, and c goes to 2 from the right. And so I'm sort of looking at 2 different values here. It's going to be 3/2, -3/2, -1 to the 2/3, plus 8 to the 2/3. That's 3/2 8 to the 2/3. Okay, so that's going to give me what I need. I just get -1 squared is 1, so -3/2. And then 3/2 times 8 to the 2/3. 8 to the 2/3 is 8 to the 1/3 is cube root of 8, just 2. 2 squared is 4. So that's going to be plus 3/2 times 4. So that's 12 halves minus 3 halves is just going to be 9 halves. That's the total. So the volume here is just going to be 9 halves. All right. So really the sort of integration is it's just about the limits. So you do these limits in there. And finally, we sort of have an idea of a comparison. So if I know something about my functions, then I can compare the two and say whether one is convergent or divergent. And convergent means it's a finite integral. Divergent means it's not a finite integral, or it's undefined, or it's infinite, right? And so I basically I'm looking at something that looks a lot like the squeeze theorem. If I have two functions that are both positive, and one of them is bigger than the other, so f of x is bigger than g of x, if the integral of f of x is finite, then the integral of g of x is also finite. So if the bigger thing goes to a finite value, then I know that the other one also goes to a finite value. So when you're doing your comparison, you basically want to say, oh, okay, I want to compare with something I know the antiderivative of. Well, maybe that thing is like 1 over x, or 1 over x squared, or 1 over x to the fourth. Well, 1 over x to the fourth converges. So if I can say that this thing is less than 1 over x to the fourth, then it's also going to converge. So that's happy. On the other side of it, if the thing on the bottom goes too big, goes to infinity, that would also imply that the thing up top also goes to infinity. So if the thing on the bottom is too big, then the thing on the top is going to be too big also. Okay. So when you're looking at this, you want to start by thinking, do I have something that is convergent or divergent? What do I think? And so you look at this thing and you say, do you think this is convergent or divergent? In this situation, maybe you don't know, but you can compare it and say, look, it's less than e to the negative x. I know that e to the negative x squared is less than e to the negative x from 1 to infinity. This is not true from 0 to infinity. So from 0 to 1, if I have like a 1/2 squared is actually a smaller number than 1/2. And so you sort of, it doesn't work out this way, but for x bigger than 1, this is going to be true. So I have this inequality. I can integrate e to the minus x. That's actually easy to integrate, right? So it's just negative e to the negative x. Do the limit as b goes to infinity, make that top limit b. It's going to flip my e to the 1 and e to the negative, e to the b, e to the negative 1, e to the negative b, because there's a minus in front of it when I do the integral. And so I sort of have a negative e to the negative x evaluated between 1 and b, and the limit as b goes to infinity. And so what I get here is negative e to the b, e to the negative b, negative e to the negative b, minus negative e to the negative 1. So I get 1 over e minus 1 over e to the b, and in fact ends up being just 1 over e, because as b goes to infinity, e to the b goes to infinity, 1 over e to the b goes to 0, 1 over e is the only thing left. Okay. So this one, it sort of limits to the right thing, and I get a finite number. Now notice, e to the minus x is bigger than e to the minus x squared, and both of those are bigger than 0. So I don't have either of these things hit 0 or go negative. And so I have a bigger function, then I have a smaller function. The bigger function is convergent. So that means that the smaller function will also be convergent. And so applying that comparison test, we say this is actually going to be convergent as well. It's finite. It didn't tell me anything about the value of it, but I cannot integrate e to the negative x squared. And so we're lucky we can at least compare it and say, well, I don't know what it's going to be, but I know it's going to be something finite. And so that's the idea. Okay, cool. And then the last thing I want to talk about is actually the kind of one really nice real application of this, and that is the standard normal probability distribution function. So let me show you what this looks like. So I'm going to show you Wolfram alpha here. The standard normal probability distribution function is the one that you learn about in your statistics classes. So in statistics, you're given a table and you're said, hey, you know, if this is the mean, and I know in my standard deviation, I can tell you within so many standard deviations, how much of the area is underneath the curve. And so what you've actually done in your probability or your statistics classes is you've got a table, and that table is telling you the thing that you can calculate using calculus, right? So they're telling you how much of the area is underneath the curve from essentially negative infinity up to some point. And in this case, I just sort of highlighted the mean there. So at 0, this is the mean, and that's going to work out. So the mean of this standard deviation, or mean of this normal distribution is 0. Standard deviation is 1. And I can always sort of adjust things to be 0 to 1 and 1. And that's how you do it in your stats class. The function that we're looking at is actually this one. So it's e to the minus x squared over 2 over the square root of 2 pi. So if I were to integrate this thing from negative infinity to infinity, what do you think I would get underneath? Well, so underneath this function, or underneath the area, underneath this curve, the total area is 1. Meaning it is 100% probable that you're going to land in one of these numbers under this curve. And so you can basically say all of the data lies underneath this curve. 100% of the data is under this curve. And so you can figure out how much is under there by integrating a portion of it. And so the integral that you're actually setting up here, the integral from negative infinity to infinity of e to the negative x squared over 2 over square root of 2 pi is just going to give you 1. So that total area is 1. So integrating any portion of that gives you what is the probability of landing within that region of your curve. So probability of landing between -1 and 1 is the integration between -1 and 1 of e to the negative x squared over 2 over square root of 2 pi. Okay. And so instead of having to go through and look this up in a table, we can actually do this potentially as an integral. Now be careful here. I say potentially we can do this, but we can't integrate this yet. So we don't know how to integrate e to the negative x squared. And that's essentially what we have here. And we just looked at it and said, well, we know it's finite. We know this integration is finite, but we can't tell you the integral itself just yet. So that's something that you have to work at, and you have to work a little bit towards later on, and you can get into it and figure out what is the actual integration of this and what is the value of this integration of the standard normal distribution between any two numbers you could possibly want. And so now you can sort of imagine there are other functions that you might be able to use as probability distribution functions. So maybe they're not all normally distributed. So most things in nature follow something similar to a normal distribution, but maybe there's something that's not. And so then you can use another distribution function as long as the integration underneath the curve is a total of 1. As you integrate from negative infinity to infinity, you're able to do this function. So you can use that as a distribution function and say, hey, the area under that curve, whatever that curve is, between any two values is how much of the data lies within those two, just those two values. And so that's how it works out. Cool. So this is the kind of the one big application of the infinity things that we do use. And it's one that's actually very applicable and pretty concrete. And so it's a very nice one to look at. All right. So that's it for the test. There was one question on this homework assignment that came from section 8.8, and it was really weird. I sort of don't know why it was on there. So I apologize. It's been taken off. If you go to try to do that one, it will say your instructor has taken this off of the homework. So I did that on purpose. It should not be there. So I apologize if you've already done it. It was a little bit tricky. It was basically asking you to do a Riemann sum, and that's definitely not going to be on the test. So I didn't want to. I threw that one out. So I do apologize. And thanks for that. Please let me know when you want to take the test. So since the test is coming up on Friday, let me know what time on Friday you're available and we will get you set up. So thanks very much.